Question one, a particle P of mass 2 kilograms is moving with that velocity and it receives an impulse of that much. Find the speed of P immediately after receiving the impulse. So I did the impulse equation and the velocity V, I've just put that as a P and Q to form the vector. Took the top line and I got P is equal to -7, and took the bottom line, I got Q is equal to 24. So the speed is 25 ms to the -1. The angle through which the direction of motion of P is deflected by the impulse. So I looked at the velocity, initial velocity, which is 4 to the left and 3 up, and then the velocity after the impact, which is 7 to the left and 24 up. So 4 to the left, 3 up, and 7 to the left, 24 up. And the angle of deflection I've marked there as alpha. So it was that 36.9. Right, car of mass 1,000 kilograms, straight line road, constant force of magnitude 400. That's the resistance, and you got a power of 16 kilowatts, and we were asked to work out U. So I did the diagram with all the figures on there. So this is constant speed. So there's no acceleration. So basically, the driving force is equal to the resistive force. So I just worked out U is 40 ms to the -1. B, the situation changes. I'll put in all the information from there, and we are asked to find the tension. Right. So I've said, I've done the equation on my F equals ma, is 16,000 divided by the instant when the speed is that much. Now that is the clue, the instant when the speed of the car is that much. So it's not constant speed, so there must be an acceleration. That's why I wrote 1600 or 1,600, which is the mass times acceleration, is equal to the power divided by the velocity at that instant, and take away the combined resistive force. Well, that looks to me like 600. Right, we did that 700. Right, anyway, so A I've worked out there because I wrote, oh, right, it is 700 is correct. In the diagram, that 200 should read 300. So that's all the working out is correct, just the diagram bit is wrong. And then I substituted it into there to work out the tension. The second equation, that's the last line, I've used the trailer where the tension is the driving force. Take away 300, not 200 according to the diagrams, 300. So F equals ma. I've used the tension comes out to be 937.5. Right, this question, I did the diagram for it, and the before and the after, and the coefficient of restitution is E, and we are asked to show that the speed of Q immediately after the collision is that. So what have I done there? I've done the conservation of momentum equation. I simplified it and I got that 2p plus q equals 4u. Did Newton's equation, q minus p over, that's the speed of separation, and the speed of approach is 5u, and rearranged it and called it equation 2. And then I did equation 1, take away equation u, which meant the q's got cancelled. And then what I did was, as it says there, equation 2 multiplied by 3. And the reason I did that was, the reason I done that was I had, you know, it says 1 minus 2. I had that in terms of 3p. So all I did was I multiplied equation 2 by 3, and then all I needed to do was, instead of 3p, I just substituted in 4u minus 5vu, okay, in brackets, obviously, and expanded the bracket with the minus, and simplified it, and divided by 3, and I got q is equal to that, which is what they asked for. And then it says, after the collision, q hits a smooth fixed vertical wall that is perpendicular to the direction of motion of q. The coefficient of restitution between q and the wall is f. Find out, in terms of E, the set of values of f for which there will be a second collision between P and Q. So I've said f is equal to W. Now W, I haven't put that on the diagram, no, which is the velocity I've labeled as it coming off the wall, right? So hitting it, the velocity of q is what we worked out earlier, and I rearranged that to work out an expression for W. Then I've said, if P, unlike my diagram, is moving in the opposite direction, Q plus P, so what I'm going to do is I'm going to look for an expression for P. So I said Q plus P is equal to 5E U. Remember previously I had Q minus P, but if P is moving in the opposite direction, you got Q plus P, the relative velocity. So you add them because they're moving in opposite directions. And I substituted for Q and expanded the bracket and simplified it, and I ended up with that. Now, if P is moving to the right and Q has just rebounded off the wall and is following it, and it's going to collide, we want the speed of Q to be faster than the speed of P. Otherwise, P is just going to get away from the Q. And I just simplified that, divided by 4 plus 10e, multiplied both sides by 3, and I got that f is greater than that. And remember, the coefficient of restitution is between 0 and 1. If you know that f has to be greater than that, then it's between that and 1. Right, you can't go over 1. Right, this question, a light elastic string, natural length 2a, and modulus of elasticity 4 mg. One end is fixed at O at the top, and the particle P of mass m is attached to the other end of the elastic string. P hangs freely in equilibrium. So when it's in equilibrium, I've just got the vital information, and I just put it at the top there. When it's in equilibrium, the actual forces are balanced, so the tension is actually equal to the weight. I rearranged that, simplified it to make X the subject, and they want from O to E. So the natural length is 2A, plus a half is 2.5, or 5 over 2A. Then it says particle P is pulled down vertically, downwards towards point A. So OA is equal to 4A. So that means the natural length was 2A. The extension is 2A as well. And the resistance to motion has a constant force of that. Now, when you read that, you know it's going to have something to do with work done against gravity, because you're going to need energy. Is going to be the work energy principle, right? So I've got X is equal to 2A, like I said earlier. The initial elastic potential energy is that, according to our formula. I just simplified it and I got 4mGA. Now, after it's moved a distance A, remember the extension was 2A, and now it's A because it's gone up A. So that's still an A remaining. So there is still elastic potential energy there. So I worked out an expression for that as well. And the kinetic energy is half mv squared. And the gravitational potential energy that it's gained is going to be mGA because it's moved up A. And the work done is the force, the resistive force times by the distance it's moved. So initially it's just the elastic potential energy that we started off with, and that's equal to all the other things, because that elastic potential energy is converted to kinetic energy, gravitational potential energy, and the remains of the elastic potential energy, and the work done to get it to there, to that point. Cancel the m's, simplified it, brought the mGA parts over to the left, and it looks like I multiplied through by 4 and then square rooted the whole thing. The whole thing is square rooted, not just the 7. Okay, so square root is supposed to be over the whole thing. Right. Particle P is now held at O, right at the top, and it's released from rest and reaches a maximum speed at point B. The resistance to motion is again a quarter mg. Find OB. The maximum speed occurs when there's zero acceleration. So that means mg, the weight, which is kind of the driving force downwards, is equal to, if you take away the tension, which is acting as a resistive force, and take away the resistance to motion as given in the question, that comes to 0. And I just simplified it by dividing through by mg, and I got x is equal to 3a over 8. And then I've said OB is equal to the 2a, which is a natural length, plus the extension where it's reached the maximum speed. Okay, so the maximum speed is where the is zero acceleration. So I use that to work out x, then added it onto the natural length, and I got 19a over 8. Okay, this question. So I've done a diagram. You're given u, but you have to have the other velocity. So it was obvious I was going to label it v and w. If there was something else, I would have called that x. Right. So what I've done there is the components of the velocity of the first sphere perpendicular to the line of the collision, where there's no e involved there. So it's just the components of the velocity. And there I've done it perpendicular. So w, notice there's no cos or sine on the w because it's just moving horizontally. And when two spheres collide, one stationary is going to move off in line with the the two centers. So w take away v cos beta. That's the separation. That's the speed of the first sphere. Divided by just u cos alpha, because the second sphere was stationary. They called it S and I think M. Oh, it's got a massive M. All right. Anyway, so that's the two equations. What have I done there? I've used conservation of linear momentum, which applies along the line of the collision. Just using those components of the velocity. I call that equation 3. So then I went back to equation 1 and rearranged it to make v the subject. So it's going to be one of those questions where we're going to turn those in equation 3 everything in terms of u, so the u's can get cancelled. So I got v is equal to that. Now equation 2, I'm going to make well, I thought I was going to w the subject, so I can substitute that. So the v is in terms of u and the w is in terms of u. So I'll substitute everything into equation 3. Every term has got a u in there, so I can divide through by u. Right, you want it to look like that. So what did I do there? I multiplied through by tan beta to get it all on one line. Okay, so the tan betas in the denominator get cancelled. And then I moved everything, well, that term with cos alpha, tan beta, I took that away or moved it over to the other side, to the left-hand side of the equals. And then I factorized because everything on the right-hand side of the equals had a sine alpha. On the left, it had cos alpha tan beta, which I factorized the other side as well. And then I divided through by cos alpha, and divided through by little m, take away big ME, right, which is what we wanted. Right, it says, given that small m is equal to E capital M, show that the directions of motion of the two spheres immediately after collision are perpendicular. So I've said like little m is equal to E capital M, and I've substituted for little m. And can you see we're dividing by 0? Now, dividing by 0 is obviously not allowed because it's going to give an answer that's undefined, which is what actually we want. And we know that the tan of 90 is undefined. So B is actually moving perpendicular to the line of collision, or perpendicular to W. Remember, W is moving along the dotted line as well. Right. Particle P of mass M is falling vertically, strikes this fixed, smooth, inclined plane. The plane is inclined to horizontal, where alpha is between 0 and 45. And then it kind of rebounds off the plane and it's moving horizontally. So I just use alternate angles to say that that's it's actually, on this question, it's actually moving parallel to the ground. So that's alpha as well. Right, so what do we have to show? Show that the magnitude of the impulse exerted on the plane by P is mu sec alpha. Right, I've used the impulse equation there. Right, magnitude of the impulse. Right, so that's what the impulse is mu sec alpha. So obviously it's going to have impulse somewhere. So started off with the impulse, which acts perpendicular to the plane. So I did the perpendicular components of the velocity. So mv take away mu, and so and the m's being factorized out, and I just simplified that. Remember, sine of 90 minus alpha is equal to cos alpha. And you know that that's 90 minus alpha by just using a bit of geometry, because if it's going to fall vertically down and move off horizontally, the angle between the two velocities there is going to be 90 degrees. So that was going to be 90 minus alpha. And then I did parallel to the slope. U cos 90 minus alpha is equal to V cos alpha. Cos of 90 minus alpha is sine alpha. And then what I've done there is divided through by cos alpha. So V is equal to U tan alpha. So I substituted 2 into the impulse. So let's just go back. So that was equation. So V equals U tan alpha is equation 2. And I substituted that into there for V, and then I turned the tan alpha into sine over cos, and factorized the U out. And then I put what's inside the square brackets in the common denominator, which is cos. So you get sine squared plus cos squared, which is 1. You got mu times 1 over cos alpha, and 1 over cos alpha is sec alpha. So it's mu sec alpha. B, it says show that v squared is equal to u squared times by that. I did this in one go. So perpendicular to the plane, we've got the speed of separation divided by speed of approach, and I just multiplied through by the speed of approach to get it all on one line. And that becomes the 90 minus alpha. The sign of that, it just becomes cos alpha. And then I did parallel to the plane. Now I think we might have already used that. V cos alpha is equal to u sine alpha. Okay, because it's 90 minus alpha, like I explained earlier. And then I did a squaring and adding the 3 and the 4, right? So v squared sine squared alpha is equal to the other side squared. And on equation 4, v squared cos squared alpha is equal to u squared sine squared alpha. And like I've done there, the sine squared plus cos squared is equal to 1. So you're left with v squared and what's on the other side. Okay. And I've factorized the u squared out. C, it says show that the kinetic energy lost by P in the impact is that. Now the kinetic energy, right, we don't need to worry about the angles. It's just it's a scalar product. So it's going to be half mu squared take away half mv squared. And v squared is what we worked out earlier, just a few seconds ago, and I substituted for that and expanded the brackets, and you get half mu squared cancelling each other out, and you're left with that. So what did I do there? It looks like I've factorized it, taking out the half, the m, and the u squared, and the cos squared alpha as well. I left the cos squared, I put the cos squared alpha on the right hand side just because I wanted it to look like what they've done. No, that's all. It could have been on the left hand side, wouldn't have made any difference. And that's what that equals. There's a D as well, which I've managed to do. Sorry about that. This question, right. So what have I done there? Of DC at the top. So I've done the Newton's equation using the perpendicular components of the velocity, and then straight underneath it I've done the parallel to DC, which is just the two, either side the velocity components are equal. And then what I've done is I've divided that top equation by the second equation, and I've got E1 tan alpha is equal to, so the U's cancel, and on the other side the V's cancel, and that was what we wanted. Yeah, that's what we wanted there. So that's part A done. Part B, it says show that E1 tan alpha is equal to E2 cot gamma, that is. Right. So what have I done there? Right, E2 is the coefficient of restitution for BC or CB. So I've done the Newton's equation all on one line, and then I've done the parallel to CB equation. Now, it's V cos 90 minus beta. So if you look at that triangle, the right angle triangle, top right, so you got 90 degrees of beta. So that angle at Q for the top triangle must be 90 minus beta. So you want the sine of that, which becomes cos beta. So I'll call that equation 1. And then parallel to CB, I've said V cos of that angle is equal to W cos of gamma. And we know that cos of 90 minus beta is the same as sine beta. So I've got two equations there with V's and W's. So I did equation 1 divided by equation 2. The V's and the W's cancelled. So, right, so I got the cos, right, I think that should say equation 2 divided by equation 1. Okay, so the actual working out again is right, but you know where it says 1 divided by 2, it should say 2 divided by 1. That's how you get that. And also we worked out earlier that tan beta for part A, we were asked to show that is equal to E1 tan gamma. And what have I done there? I've divided, no, what have I done there? I've substituted for tan beta. So tan beta is E1 tan gamma. So I replace the tan beta with E1 tan gamma and then multiplied both sides by E2 to get what they were asking for. Okay. Oops. All right. Looks like I missed out C. Okay. Well, that's for another time.